Good afternoon, everyone. It's very nice to be here. As you heard at the beginning of the introduction of this event, this is in the framework of a workshop that's taking place during the week dedicated to the relation between invisible and visible. And so I decided to dedicate my presentation precisely to this relation, bringing together both science and art. When it comes to discuss the relation between art and science, and especially here in Spain, it's unavoidable to think of Salvador Dalí, who best represents the inspiring power of science on art, and in particular, who was explicitly fascinated by the relation between invisible and visible. So this is a statement from his programmatic manifesto, Antimatter Manifesto, where he says that today the exterior world and that of physics has transcended the one of psychology. At the beginning of his career, he was mostly fascinated by psychoanalysis and by Freud's theories, and now his new father is Heisenberg, who was has been one of the fathers of quantum mechanics. So I will be using part of the artwork of Salvador Dalí to guide you through this trip into the relevance of invisible in the development of science. And one of the best ways to bring together and to show the unity of art, science, and the natural world is to look at a picture of a night sky. This, of course, needs a dedicated telescope to be seen, but it's just mind-boggling, the beauty of this image. There are thousands and thousands of galaxies. There are more stars and planets in this picture than there are grains of sand on a beach. And of course, the sky has fascinated the scientists, has fascinated the artists, the philosophers. Dalí himself dedicated to the sky some of his pictures. From the scientific point of view, looking at this picture, aside from the beauty, is particularly interesting because there is something in that picture which in fact is not really visible, and that becomes the most interesting part of it. And it's the existence there of dark matter, of matter that does not radiate and that therefore we cannot see. Now, this comes out of this phenomenon called gravitational lensing, by which a cluster of galaxies, like the one we saw in the previous slide, would act as a lens, would curve light going through it. So if we are sitting here observing the sky, this is a cluster of galaxies like the one we just saw, and behind that we do have other galaxies. As the light comes to us, it goes through this lens and gets deflected in the same way it would happen going through a glass. And this is one of the predictions of Einstein's theory of relativity that Alvaro just mentioned earlier. So the outcome of this is that by looking at the deformation of light, we can infer the actual amount of matter that's included in this cluster of galaxies. And the conclusion of that is that, as we see, there are very distorted shapes which represent the distortion of light going through this cluster. And the conclusion of it is that there is much more matter in this cluster than we can actually see. And that leads to this idea of the existence of dark matter. So what we learn from this is the following. For something to be declared invisible, we must know it's there. And if we know it's there, it's not truly invisible any longer. We wouldn't call invisible something that doesn't exist. We would call invisible. Invisible is an adjective, and it's an adjective that applies to things that exist. And therefore, we just simply have to learn how to work with what is invisible. Now, this idea was very clear to Dalí. This is one of his paintings from the 30s. It's called Surrealist Composition with Invisible Figures. All of the titles that you will see are the original titles translated into English. So they are not my invention, they're not my rendition of the picture. It was his intent to call it like that. And you see here there is a chair, there is a bed. There are no figures here, but we do see the trace of someone being sitting there, being invisible. And it's precisely because of this that we can claim that there is an invisible. Proving the existence of the invisible, namely providing evidence that there is something where there appears to be nothing, turning the invisible into visible, is one of the main drivers of scientific progress, as I will try to explain to you. In particular, this making the invisible visible is a process that takes us from the realm of magic and superstition to the domain of science. To acknowledge that if somebody gets sick, it's not because there is some malediction that's being sent by a god, but it's because there is some invisible animal, some virus that's affecting him, is exactly what makes civilization progress. Now, this is another of the invisible pictures of Dali. It's called the invisible harp. So this is a bit harder to understand than the previous one. It's not obvious that there is anything invisible here, and it's even less obvious that it's a harp. So besides recognizing the existence of the invisible, one of the key steps is to establish the nature of the invisible, what it is that we're dealing with. So as scientists, we phrase this in terms of what are the invisible forces that tie things together. Here there was supposed to be, oops, no, an image that is not appearing. So this is related to one of the first slides by Álvaro before, understanding the difference between gravity, where there is absolutely nothing apparently holding the moon together with the Earth. And how many of these forces are there? How do they work? And what is hidden inside things? What are things ultimately made of? So the goal of modern physics is to unveil the invisible, give it substance, and explore its consequences for the life of the universe. So we ask questions like what and how, what is nature made out of, are there fundamental building blocks, a bit like the Democritus and the ideas of the atom, how do these atoms interact, and how they determine the properties of the universe. And asking these questions has been the job of physicists for many, many years. And since the last 30, 40 years, we do have a framework which we call the Standard Model of Particle Physics that gives an answer to those questions. I assume, certainly you know that matter is made of atoms. Atoms are contain a nucleus. In the nucleus, we have protons and neutrons. And we discovered that protons and neutrons themselves contain quarks. And for all we know, we stop there. Quarks are absolutely elementary. There is nothing in them. Of course, nothing prevents even quarks to be composite, but that is not the evidence we have today. And then there are electrons going around the nucleus. And the quarks, two of these quarks are sufficient to describe the protons and the neutrons that we observe in nature. And with the electron, we can complete the picture of the stable matter that surrounds us. It turns out that these, what we call a generation of quarks and leptons, is repeated 3 times. There are more complex objects, heavier objects, in fact. They're not more complex because they have exactly the same properties as these fundamental quarks. And these objects are part of the exploration done in experiments like those at the LHC. So what I will do now, I will just go through a few, I will not try to explain to you how physics work, how the Standard Model work. I will just go through a few anecdotes on the role that invisible played in the discovery and in the understanding of fundamental particles and interactions. So it's really meant to be entertaining and not an educational. So in the late 20s, there was one of the first most important puzzles of the invisible in the context of particle physics. There was a nucleus, helium-6, unstable, known to decay to another nucleus, lithium, and to an electron. Now, if these were all that happened in such a decay, there has to be energy conservation, and energy is simply the difference in mass between these two, so the electron would have a fixed energy. But that was not the case. There were decays in which the electron was very, very slow, and they were observing decays in which the electron was actually very fast. So the electron energy varies, and therefore that led at the very beginning to even accepting the possibility that energy may not have been conserved. Until this person, Pauli, proposed a much more credible solution to this puzzle, namely proposed that there was, in fact, a third object involved in the decay, an invisible particle, the invisible neutrino. And this explains things very easily, because then if we have helium decay to lithium, electron and neutrino can share the energy equally, and therefore the electron carries some energy. But we can also have decays in which the neutrino is very slow, little energy, and most of the energy goes to electrons, so the puzzle is solved. Now, it took 20 years for neutrinos to really be observed. In other words, for neutrinos to trigger a reaction in which something could be detected, observed directly, okay? But nevertheless, people for all of those 20 years accepted the existence of neutrinos, even though they couldn't see them. This is just a picture taken much later from the 70s of the way in which a neutrino manifests itself. Nowadays, we observe neutrinos using experiments like these. This is Super Kamiokande in Japan. It's a huge tank, 100 million liters of pure water. You see this tank. Here is a little boat with a couple of people, of physicists on it, working on all of these, you see all of these objects, which are photomultipliers. They are objects that detect light. Just in case a neutrino decays, it generates light, and a picture will be taken of it from all of these cameras. Now, the neutrinos that such a detector can see are neutrinos produced, for example, from cosmic rays. The whole Earth is being bombarded continuously by particles coming from the skies. They interact with the atmosphere, and they give rise to the production of many particles, some of which eventually decay to neutrinos, and neutrinos go through the detectors. What happens is that the neutrino comes into the detector, interacts with water, very rarely, because neutrinos, we don't see them because they interact very, very little. And once the electron is produced, it's traveling very fast inside the water, and it just radiates. It gives rise to something like the supersonic beam of an airplane moving faster than the speed of sound. And it's exactly this sonic boom which is detected in the form of these rings. This is just the cone of the sonic boom of the electron moving through the water. So you see which wonderful picture. I mean, a picture like this, you don't know whether it's coming from science or whether indeed it's coming from an artist. One of the amazing consequences of neutrinos being invisible, and they're invisible because they interact a little, it means that they can go through things. And in particular, they can go through, for example, the whole sun. The sun produces neutrinos as part of its energy generation process, and it produces them in the core. The core of the sun, the very center of the sun, almost 1 million kilometers deep into its surface, is completely invisible. The light that's produced there just doesn't come out, because it's like pretending that light comes out of a mountain, right? So the only thing that can actually go through the sun and come to us is neutrinos. And this is a picture of neutrinos coming from the center of the sun, detected with an experiment like the one I showed before. So we get to this almost paradox that the more invisible you are, the more capable you are of making visible what would otherwise be invisible. So there is an interplay here. Now, neutrinos, of course, fascinated Dalí very much. In his Antimatter Manifesto, he makes explicit reference to them. He says it's with pi mesons and with the most gelatinous and indeterminate neutrinos that I want to paint the beauty of the angles and of reality. Now, we said everything about neutrinos. Shall we say something about pions? Do pions reveal something interesting for our discussion of invisible? So pions are these objects, they're called mesons, and they're made of a quark and an anti-quark. So it turns out that these objects, and quarks in particular, are really the ultimate invisible, because neutrinos, after all, even though rarely, but occasionally, we can see them, as I proved, because occasionally they do interact. But really, quarks, there is absolutely no way we can look at them individually and take them out. And the reason is the following. If we take, for example, a pion and we try to pull apart the quark and the anti-quark, we have to put energy into that. And at some point, this energy, by using Einstein's equation E equals to mc squared, gets turned into yet another quark-anti-quark pair, as it's shown here. I pull them apart, a lot of energy builds up here, I create a pair of quark-anti-quark, and here I have then the elements of one pion and the elements of another pion. So if I try to separate the pion to get the quark and anti-quark, what I'm left with is two pions. And if I replicate the process, I keep getting more and more and more pions. So the result, in fact, of any attempt to break pions, which is a way of what you would like to achieve by colliding, for example, protons at the LHC, is just generating a large number of pions. And it's interesting. There is this picture, again, by Dali, well before quarks were introduced, but certainly pions were known. This is a saint surrounded by 3 pi mesons. And, you know, there is little to laugh, because if you look at the reality, what you get is this picture. Whoops, sorry. So this is the art, and this is the real life. This is a picture of, say, a proton colliding with a system, and a picture being taken of what comes out. And as you see, there is an incredible similarity between the two. And this is certainly much later than 56. So some of the main open questions in our field, and again, how they relate to the world of invisible. Now I have more sympathy for Alvaro's inability to turn the slides before. Now I see the problem. Everybody should try it, and then you will understand. So one of the big questions is, what is the vacuum really made of? Does complete full emptiness exist? That's the ultimate of the questions about invisible, right? I mean, can we create a region in the universe in which there is absolutely nothing whatsoever? And the answer is no. The Higgs boson itself is that was discussed by Alvaro before, is the proof that nothingness doesn't exist, because the Higgs boson is precisely the excitation of the vacuum. We go into a region of space where there is absolutely nothing, and if we inject sufficient energy with sufficiently heavy probes, we immediately stimulate the production of these Higgs. It's a bit like me clapping my hands and generating waves in air. So air is invisible. We know it's there because we breathe, but otherwise, you know, we wouldn't be aware of that. But we can be aware of sound. So sound, the Higgs is exactly like sound in a sense. And it's amazing that, again, Dali had foreseen this in a sense, because in 1935 he produced this painting called The Echo of Void. And The Echo of Void is really, in 4 words, the best possible, if you wish, image that we can have of the Higgs boson. What's the origin of invisible dark matter? I introduced dark matter before. I hope, and I'm sure that Carlos will discuss more about that perhaps in his lecture. And, you know, the complexity of these pretty much characterizes the complexity of finding an answer to this question, an answer that we still don't have. Whatever happened to the antimatter in the universe? Antiprotonic assumption, again, a work by Dali just before antiprotons were first discovered. Why do we live in 4 dimensions? The question here is whether there are more hidden and invisible dimensions of space-time that, you know, are intangible, they are invisible, but still they're there. And as you know, many theories talk about that. And this is something that even in the last days of his life in 1979, 79 led him to make a drawing on the search for the fourth dimension. So Alvaro gave a wonderful introduction to the LHC. I would have just spent a few words to illustrate it, but there is no point in repeating it. This is the tool that we use to go after those questions and many others. There is an intrinsic beauty and art even in the conception of these experiments. And certainly what comes out of them, the pictures that you already saw in Alvaro's presentation, they can occasionally very hardly be distinguishable from pieces of art. This is El Fox Artificials from 1922, and tell me the difference, right? So final remarks. The depth of our understanding of nature has reached really very new levels, uncovering the existence, the origin, and the role of many invisibles. And the progress continues on the remaining big questions. And of course, there is the understanding in all of us that there will always be, however, a new layer of unknown invisible, which is the invisible hand of nature that decided that, after all, there should be something instead of nothing. Thank you.